Okay, is that okay? I can hear myself on there. Like to welcome everyone in the audience here today in this ETech building, and I'd like to welcome those who are online. Just before I forget, in particular, those online, if you have questions, please can you type them in the chat, and we'll catch up with them either during or at the end, probably at the end of the talk. But before we start with the main attraction, which is Bruce Bailey, I did want to say a few words about Ray Falconer, whose name is given to this seminar series, and just a few notes. And I think there are several people here who probably did know Ray, so I definitely knew Ray. So Ray was often referred to as Mr. Weather. From his early days as a weather observer atop Mount Washington, New Hampshire, to his work at the General Electric Research Laboratory, Ray was an enthusiastic disciple of the atmosphere. In 1961, when Vincent Schaefer established the Atmospheric Sciences Research Center, he hired Ray as his first member. From that time on, Ray's boundless energy was poured into public education on weather and the environment. His popular radio weather commentaries, his articles, and his lecture series made him widely known as the voice of the ASRC. Ray started this series in the summer of 1962, so soon after he arrived, where it started at Whiteface Mountain as a summer series. And in 1973, he expanded it to become a spring series here on the University at Albany campus, which is where we are in this series today. The series is deeply rooted in ASRC's history and offers scientists a unique opportunity to engage with the public. Indeed, we have a strong slate of talks coming up this season. And I'd like to give a special thank you to Dr. Craig Ferguson and his committee for establishing this excellent slate of talks. Before I introduce our speaker, I did want to take this opportunity to say a few things about the center. I realize that many in the audience, not everyone, but most people in the audience are aware of what's going on, but I know there are people online as well that may not be. So we started in 1961. We have 14 faculty, 20 students, 27 research scientists and postdocs, and 10 administrative and technical staff. We cover a wide range of weather, climate, and environmental issues, including renewable energy, wind and solar, and grid resiliency, the topic of today's presentation. Various aspects of weather and climate, including climate modeling, numerical weather prediction, sensors, streams, boundary layer meteorology, including air-sea interactions, land-atmosphere interactions. There's a growing emphasis on the use of artificial intelligence, machine learning, in various applications, air quality and atmospheric chemistry, and there's been an increased interest in the center, including with a new hire coming this summer in urban weather and climate. We have a number of resources that support our research mission. Whiteface Mountain Laboratory is uppermost in those. We've been making measurements there for more than 50 years in terms of atmospheric chemistry, cloud processes, etc. We're proud of the New York State Masonet, a network of weather stations across the state, serving various aspects of weather sensitive areas, including state agencies as well as the private sector. We have a Center of Excellence. $8 trillion, or 39% of the total US GDP, is estimated to have some weather sensitivity. And our Center of Excellence is able to help provide solutions to those private and public sectors that have some sensitivity in order to deal with it better, using our data, using our talent at ASRC and the Department of Atmospheric and Environmental Sciences, and obviously using various analytical and modeling tools. We also don't look at the numbers. They're all big numbers. So we're very proud of our Excite laboratory, which is arguably the strongest sort of AI machine learning infrastructure on the campus, if not in the region at the moment, to support AI machine learning activity and data visualization. And finally, just want to celebrate the fact that we're in the ETech. ASRC moved in here in September, but it's just a dream come true for many of us, all of us. And just want to reiterate the amazing opportunity that we have here to carry out interdisciplinary science, as well as ASRC and the Department of Atmospheric Environmental Sciences. We have the College of Emergency Management, Homeland Security and Cybersecurity, the Mesonet, the Center of Excellence, the National Weather Service, environmental engineering, business development, and Excite Laboratory. It's an amazing cocktail of interacting entities that are really going to power our research for the future, I think. So that's my end of that. Okay. So now it gives me great pleasure to introduce today's speaker. And Bruce and I go quite a long way back, and it's been a pleasure interacting with him over the years. And just let me introduce Bruce to you. So Bruce earned his undergraduate degree in meteorology from Cornell University and began his career in the renewable energy field while working as a research associate at ASRC. And it would have been really remiss of me just not to mention that Bruce was employed at ASRC originally by Ray Faulkner. So it's an interesting coming around here. After leaving ASRC, he founded and led AWS True Power, a meteorological and engineering consulting firm serving the renewables industry for over 30 years before the firm was acquired by UL, where he became the vice president of renewables. Bruce retired from UL a couple of years ago, but stays professionally engaged by writing, serving on boards, and reviewing technical articles for a peer-reviewed journal. He is actively involved and collaborates with us at ASRC today, and has also established the Bruce Bailey Fellowship to support a doctoral fellow focused on renewable energy and grid resiliency. And just on a personal note, I've always enjoyed the collaborations and the conversations I've had with you, Bruce, and I just am enjoying the collaborations going forward. So it's a great pleasure to have you here today. Let's do this one.
Okay. Thanks, Chris. And good evening, everyone. It's a pleasure to be back to ASRC and reconnecting with everyone, old and new friends alike. I'll be talking about just the dynamics of renewable energy and how weather science has interacted with that field, since that's been the arc of my career. With the nonsense going on, say, in Europe now, with the war in Ukraine, and it's brought up a lot of questions about over-reliance on fossil fuels and where those fuels derive from. And it harks back to the mid-70s when there was a similar type of situation when there was an oil crisis, and prices went through the roof. They went up above $1 per gallon, and that was a major crisis for the United States. But that was back in the mid-70s, and that's when I started my career at ASRC. And that's when renewable energy got launched, the modern era of renewable energy, nearly 50 years old, but that's quote unquote modern because new technologies take a long time to mature. Ever since it started, it was clear that weather science plays a significant role in renewable energy. After all, wind and solar are weather phenomenon. Hydro is weather driven as well. But it was also clear that as renewable energy technology matured, so would the various applications for weather science or meteorology, and the application of weather science to different disciplines that are involved in renewable energy. Things like project development and project financing, grid interconnection and policy development, all rely heavily on weather science. And that's been an activity that I've been involved with for many decades now. So I just want to share that experience with you today. And that's generally the nature of my talk as well. First, let's take a look at the trending of energy use, particularly for electricity production here in the United States. This graph was put together by the Energy Information Agency. And for the last decade or so, renewables have been the largest source of new electricity sources here in the United States. Renewables are shown here in green. at the top portions of the graph. Wind and solar are the most active renewables, and they constitute now about 11% of our electricity here in the United States. But when you throw in hydro, plus the small amounts of biomass and geothermal, renewables constitute 21% of our electricity. Going forward, the EIA projects under its reference case that renewables will constitute about 42% of our renewables, of our overall electricity needs. But in that same time frame, electricity is going to grow by about 30%. And most of the growth in renewables will be primarily wind and solar. So both of those technologies will have to quadruple in capacity in the time period between now and 2050 to meet that target. Of course, the factors that have been helping to promote renewables are pretty self-evident. You're all pretty much aware of them. Favorable government policies and incentive programs, technology advancements, which have helped make the wind and solar more efficient and more cost-effective. Environmental factors and drivers like climate change and clean air, and then weather science as well. And that's really played a very enabling role for renewable energy. And I'll talk more about that with some illustrations coming up. First, let's talk about the life cycle of a typical wind and or solar energy project. And I'm focusing largely on large scale projects. There's the development phase, operations, and what's called repowering or life extension. And we're seeing more of that happening today. And that latter category applies to projects that have been operating for perhaps half their lifetime. And it's maybe time to update major components of the projects, maybe replace the project altogether. And what all these three phases have in common is their strong reliance on weather science, and they do so in different ways. In the development phase, as you can imagine, looking for the windiest and the sunniest sites, that then entails a lot of research and measurements. There's ways to lay out projects so that they optimize their energy production. And there's other steps that are very weather sensitive as well. They're in the operational phase of projects, and projects are designed to have a minimum lifetime of at least 20 years, but in reality, they can go 30, 40 years and perhaps even longer. But maintenance activities, optimizing the performance of the projects, forecasting production so that it can, the output of these projects can readily integrate into the grid. Those are all very weather sensitive factors and quite sophisticated these days. And then lastly, the repowering and life extension aspect, it's very similar to the development one because you're typically looking at new technologies. You've got to look at the performance, you've got to look at economics. You probably have to go and re-permit the project in many cases, but it's just that cycling of projects and going forward. Now, the renewable energy world consists of many stakeholders, and it's very multidisciplinary. And these various stakeholders play important roles in transforming the energy economy to make it greener. And if we start off with, say, developers and operators, they're the main character, they're the protagonists in this main story. They've got to work with all the other stakeholders in order to make their projects happen. Go backwards. And they also need to collect all the relevant weather information to address all their project assessment needs, but also to address all the assessment questions that all the other stakeholders are going to be having as well. Policymakers and regulators, of course, they play the role in establishing policy and the incentive programs, permitting the projects. And I'll be giving some examples too, in terms of how weather science has helped driven policy on a state-by-state basis here in the US. Utilities and transmission system operators, they receive all the output from these renewable energy projects, and they need to know what's coming in advance. They also have power purchase agreements, interconnection agreements, and there's a lot of technical details that are very weather sensitive as well. Manufacturers, particularly large-scale wind turbine manufacturers, they won't sell you a turbine until they really understand the site where you want to put the project in. They want to make sure their warranty isn't violated by the environmental conditions experienced at the site. Some sites are relatively benign, some are quite robust. And of course, banks and insurers play an important role. Banks capitalize the majority of projects, and they're very risk averse. And I'll give an illustration of just what their role is and what their parameters are. Insurers are very important players as well. Projects being weather sensitive to extreme weather events, large hail, wildfires, extreme winds. To what degree are those incidents covered by the warranty of the equipment vendors? How much of that is covered by the owners and operators? So insurers play an important role and really need to understand the risks involved to these projects from weather phenomenon. Of course, underscoring all of this activity is the need for effective science communication with a variety of stakeholders. And they need weather information translated into their language, into their worlds, and translated to their metrics as well. So you can see just sort of the family of terms that need to be understood by the meteorologist in order to address all the needs of the various stakeholders. And over the years, this has been a very iterative process as well as one that's been very collaborative. You really got to understand their world. They need to understand your world. And that takes a long time to do. But once you make it click, then things happen. And that's why renewable energy is growing so healthily and so rapidly, is that there's a broad level of understanding and collaboration across the sectors. Now let's talk about zero in and look at three particular aspects of how weather science impacts projects, different aspects of projects. First, we'll talk about the project development cycle. And one distinction I want to start off with, and it may not be known to everyone, that's just to understand that comparing wind and solar, if you look at the solar resource, if you increase the resource by, say, 26%, then the power available in that resource also increases by 26%. But wind, if you increase the wind speed by 26%, the power does not increase by 26%. It goes up by 100%. So it's an exponential or cubic relationship between wind speed and wind power. And so that demands exacting measurements for wind. Solar is very exacting too, but you don't need as many solar monitoring stations for a large scale project. Typically 1 or 2 stations is all you need. But for wind, you need multiple tall towers, you need redundant equipment, LiDAR, and other types of technologies to measure the wind. But then you don't measure wind at all the locations where you may be putting up wind turbines. You'll put up equipment at a subset of sites. You want to do that for economical reasons too. And then you use atmospheric models to translate that data into full atmospheric predictions of what's happening together with the underlying surface roughness conditions, undulating terrain, and so on, to come up with long-term wind projections for a project area. Whatever you did, it stopped from advancing. Must have been the finger that worked.
I think the mouse was hovering over that.
That's where the mouse was. Anyway, so just that process can be capsulized in these 6 steps. And I'm talking a little bit more about wind here because of its nature of requiring more intensive types of measurements. But typically a project in the development phase will start off with selecting sites, the number of sites, and measuring for at least 1 to 2 years. And then converting that short-term data into some long-term statistics through some correlation analysis with the regional reference stations. And then let's say for wind projects, you want to adjust the wind conditions up to the hub height of the turbine that's in question. It may be 100-meter hub height, 120, maybe 80 meters, whatever the case may be. And that's across the entire project area for every single turbine that you're considering. Then you're translating wind data, temperature data, air density data into power using a wind turbine's power curve. And then you apply losses. They're typically 15 to 20% for either a wind project or a solar project, and to come up with a net annual energy production for the project. But you just can't stop there and make the decisions about how to go forward with your project, because you really don't know how certain or uncertain all your measurements and assumptions and translations have been during the process. So there's a step involving uncertainty analysis. And it's not only the developer that needs to understand uncertainty, but also the manufacturer and the banks. And they look at uncertainty in different ways, and they use the information differently, as I'll illustrate. So just a little chart about uncertainty analysis. And that's an evaluation of the various elements and the uncertainty associated with each one of them that are associated with your measurements, your model output, and all of your assumptions. And typically, the uncertainty is expressed in a normal distribution here, with the middle of the distribution called the P50, P meaning probability. And the P50 simply means that the probability of the actual energy production, annual energy production, being above the midpoint value is 50% or below that value 50%. So that's sort of the most likely value. It's called the P50, and that's the number that developers tend to rely on mostly because that helps to decide or dictate what their cash flow will be for the project. Bankers, on the other hand, will look at the P99. They're very risk averse, and they want to look at those situations where either wind output is particularly low in a given year or project expenses are particularly high. They want to make sure that you can pay the debt service each year, at least 99 years out of 100. So they're going to size the debt for the project based on the amount of uncertainty in your projections here. So long story short, the more investment in equipment, and I'll say in weather science, just there's lower uncertainty, and the spread of the curve is much narrower, and the amount of capital that can be raised for a project is much greater. If you do have high levels of uncertainty, then the developer is going to have to come up with more cash themselves. And projects these days are typically, hundreds of millions of dollars easily. They're now, easily $1 to $2 or $3 billion. Offshore wind projects, even bigger than that. So we're talking about big money as well. The information on the right side, when we're looking at, say, debt sizing, but really some of the parameters that a bank will use will be something like what's called the debt service coverage ratio, where they'll look at the cash flow coming out of a project and compare that with the debt service. Debt service just meaning paying off the principal and the interest on that principal every month, every year, and making sure that there's a ratio there of at least 1.35 greater. There's lots of other metrics as well, but working with banks over the long term and really understanding their various metrics, then they've been far more supportive of financing more projects going into the future. Now let me shift topics and talk about policy and how weather sciences have had a role in helping states primarily be very proactive in encouraging more renewables. Mapping of wind or solar resources typically done in two different ways. One is very local scale for a proposed project, and I just talked about that in the last example, where measurements are translated into what the resource is across a project area, and then translating that into energy production. But the other approach is doing mapping on a statewide basis or even a countrywide basis. And this is done and has been done to help inform policymakers to understand how much renewable resource they have within their jurisdiction, where it's located, and then there are other tools as well that I'll talk about. And when I talk about mapping, it's not just coming up with an annual average resource at a certain height above ground, but there's a ton of underlying statistics, which looks at frequency distributions. It comes up with hourly time series data, typical meteorological years, and you can really zoom in to this property here on a map like this. You can do so electronically and just extract a whole body of rich data from which you can do all sorts of project planning. The mapping process involves a lot of meteorological analysis using numerical weather simulation models that rely on historical full atmospheric databases called global real analysis databases. Surface properties, land and water surface properties are included in the modeling, and ultimately you generate weather and power data sets that are derived for each grid cell. So you can create a very high resolution database for the region of interest, typically a kilometer or finer in resolution. And then what's cool with the mapping process with geographical information systems is that you can overlay the maps with all sorts of other information you want to use. Locations of existing power lines, roads, sensitive land use, population centers, whatever the case may be. You can do all sorts of other analyses, financial ones, such as the cost to extend a transmission line a certain distance, to help decide, okay, where's the lowest hanging fruit, where it's easiest to put projects, where might it be more difficult to do so. Now, my company did the first wind map for New York State on behalf of NYSERDA, but we also did the first national map on behalf of the US Department of Energy. We've also worked with the World Bank and the United Nations, and we've mapped the entire world, and we've remapped the entire world as well, both in wind and solar. States have been using these maps to help develop their renewable portfolio standards, the targets they establish, whereby they want to guide the states in terms of how much renewables, how much of the electricity they want to come from renewables by a certain target year. So for New York State, for example, there's the current goal is 70% renewables by 2030. And most other states have targets as well. We've worked closely with various other entities over the years, a very strong public-private collaboration to help promote adoption of the maps, but also over the last 20 years working, say, the Department of Energy to help states adopt proactive renewable energy programs. Most of them have them in place now, but it was an interesting effort which also helped establish credibility for our company. For example, as we did maps for regions of the country or on a state-by-state basis, we then collaborated with the National Renewable Energy Laboratory, NREL, and they would independently validate our maps. This was done by their set of meteorologists. For any differences that they reached from our conclusions, we would then have a discussion, and we would then negotiate, if you will, and come up with final maps. They became the official federal maps. This is for wind in this case, and then they were co-branded as well. NREL got a bigger logo than we did, but that's okay. But DOE, paid for this activity. But we also had lots of state meetings and other stakeholders within those states, as you can see here, to help get a lot of people accepting renewables and then deploying renewables and then learning from renewables and then, things just evolving over time. The third area I want to talk about is grid integration and the role of forecasting for both wind and solar. Now, forecasting of production of any large-scale generating plant is essential. It's done all the time, and the independent system operators across the United States need to get forecasts of availability as well as future output from projects, from generating plants, be it solar, wind, or be it nuclear, coal, and the like. And utilities need to deal with unit commitment and economic dispatch decisions. And these forecasts are considered real-time or same-day forecasts as well as next-day forecasts. So it's like what's happening now or the next several hours, but also planning over the next day or two so that the appropriate facilities are standing by and ready to generate power when needed. Of course, at the same time, utilities need to make predictions of demand, how much is going to be used. And so they're always in that balancing act of matching supply and demand. I would say forecasting has probably been the single most important factor or enabler of the growth of renewable energy. 15 years ago, we did a study with New York ISO, NYSERDA, GE Consulting, to look at the state of the art of, say, wind forecasting and just the economic value of wind forecasting for grid integration of wind power. And it was found then that the quality of the forecasts were 85% of perfect forecasts, and that they were highly valued. They saved the grid operators tens of millions of dollars per year. And so it's just integral now that the trust and quality of forecasts, but the trust in those forecasts by utility operators is so strong that it has enabled lots more renewables to come onto the grid without sacrificing reliability. There we go. The forecasting process, again, it's very similar to the weather forecasting. There's a sequence of regional and the mesoscale and local models that also feed into statistical models, and through experience, they get smarter via machine learning. There's a series of model outputs, which are then fed into an ensemble model, which is then fed into a solar project model or a wind project model, translating the solar and meteorological variables into solar output or wind system output. And then the forecasts are produced in different formats. Deterministic, like what's it going to be tomorrow, 550 megawatts at 2:30 in the afternoon, or probabilistic, that there's a certain probability that there'll be 550 megawatts at that time, or there's other outputs as well. So there's different ways to project this, and this has all evolved over time. Of course, forecasts are not rendered all the same. There are situational forecasting approaches well in play, and processes are tailored to, say, the time frame. Are you forecasting over the next few minutes or few hours or the next few days? And very different tools are used. There are also forecasting approaches for critical events, such as extreme weather or ramp events. And a ramp is defined as a rapid change in generation over a short period of time. And that ramp can be an upward ramp or a downward ramp. And that's becoming a bigger issue, as I'll discuss in a moment. But first, just to give you an example of how different forecasting tools are used, say, for solar forecasting. We're looking, say, on the bottom axis here, looking from time periods of next several seconds to the next several minutes or hours or days. Different tools are generally relied upon. For the very, very near future, of course, persistence, what's happening now is very likely to happen a minute from now, for example. But there are other tools such as sky imagers that are cameras that look upward, look at sky patterns and how those clouds move. One can estimate the solar resource impacting solar projects at the time. Satellite imagery as well can be used to translate predictions of near-term solar radiation reaching the ground, and of course numerical weather prediction models as well. So there's a whole slew of different modeling and analysis techniques to help address the different timeframes for forecasting horizons. This is a messier slide, but this is illustrating the issue of ramp events, which come about not only from short-term weather events or approaching cold front, that sort of thing, but also with the natural daily cycle, particularly for solar. What's being shown here is, let's say, if we look at the upper two curves, the blue and the red colored curves, we're looking at a utility load, the demand for electricity from the transmission system. This is for California in January of 2020. So I've got a whole month shown here. And we're just looking at 24 hours in a day. So the top blue curve represents the typical demand for electricity over the course of a day. Low at night, and use the mouse here if I can. I can't see it here. In the evening. Down below, the blue or blue-green, that's a wind output, which is fairly steady during the course of the day. And the yellow is showing solar system output, all the solar that's involved in the state as well. Not just large-scale solar projects, but rooftop residential and commercial systems as well. And what is being shown here is sort of the net result is the net load, which is shown in red here, is how the demand on the grid, the electricity from the grid, goes way down during the middle part of the day when there's a lot of sun available. And a lot of electricity is being produced on site at homes and commercial buildings, behind the meter, in other words. So the demand on the grid decreases very rapidly in the morning hours But then when the sun is setting, then it ramps up very sharply in the evening. And this illustration here shows, a typical up ramp of 12,700 megawatts. That might be 15 large scale power plants or more. But having them come online or ramp up in just 3 hours. And in the morning, taking large systems and taking them offline. That's in a situation that utilities weren't designed to do, to have these big changes over short periods of time. And that's an outcome of lots more renewables, that there'll be more of these ramping events that need to be managed by utility systems. And there are ways to mitigate this. Battery systems will be one of them, but there will need to be more flexible generating resources on the grid in order to accommodate these kinds of changes. So it's a real challenge for grid operations going forward, but we can go forward with our eyes wide open. So looking to the future, and with lots more renewables, there's going to be lots more dependence on weather science as well. And I want to talk about that in 3 different ways. Expanded forecasting, also offshore wind, and then talking a little bit about smart buildings and cities. First, expanded forecasting, I just talked about it, but with more distributed energy resources. These are the resources that are not connected directly to the grid, but are located pretty much on site where the uses are, see in the distribution system. Forecasters need to forecast how all those distributed projects are operating, not only now, but over the next several minutes and over the next couple of days or so. And that can be, but you're not monitoring those systems directly. So you have to estimate that, you can simulate that. And that's very doable, but that's just going to grow larger and larger. There's also going to be a demand for forecasting when batteries are charged and discharged. These are grid scale batteries. Another aspect, a growing need for forecasting is to understand the impact, say, on solar projects from increasing incidence of wildfires, not only in the Western US, but in places like Australia, where they had massive fires a couple of years ago. In the summer of 2020, solar output decreased by 20 to 30% in some parts of the state during peak hours due to wildfires. Forecasters have to simulate this and forecast this. And smoke from these fires has had measurable effects on solar projects as far east as New York State. Most large-scale solar projects have tracking, one-axis tracking systems, and trackers need to be stowed during high winds or during threats of large hail. So getting forecasts of those kinds of conditions are needed as well. And then denser weather observation networks like the New York's Mesonet will be very important in helping to do a better job at addressing short-term weather events and how weather features are migrating across the state. Networks will just help with short-term forecasting dramatically. Offshore wind is something that is pretty familiar to folks living in Northern Europe or Eastern Asia, but not so much in the United States. But offshore is just beginning to take off here in the US, and it'll actually outpace and eclipse land-based wind east of the Mississippi within the next 10 to 15 years. The thing about offshore wind is that there's very little offshore data and it's very expensive to gather. So most information about conditions offshore will be developed from modeling approaches. There's also the important feature of coupled meteorological and oceanographic met-ocean variables, sort of wind and wave impacts on foundations and towers and structures. And those need to be well understood. Also, the offshore environment is far more severe than land-based wind projects. So really understanding the risk that's being taken for these offshore projects is essential. And then lastly, this is a little more futuristic, but some cities are getting there now. But with the Internet of Things, with much better communication of devices, we're just seeing more and more, at least ideas being deployed for smart buildings and cities. After all, 70% of the electricity use is in buildings. Also, the majority of the world's population lives in urban areas, and that's only growing. So there's going to be more pressure to address energy needs in urban environments or in the built environment. So how do buildings interact with the outdoors, with the atmosphere? So there are more advanced energy management systems. There's more deploying of weather sensors within cities and building environments to really understand microclimates and to help optimize performance of, say, building energy systems. More buildings, too, are investing in their own microgrids or battery systems or on-site solar and battery, whatever the combination may be, just to increase their reliability of power, because there's less trust in grid power being reliable going into the future. And so there'll be a greater demand for more of an interplay between building-based energy systems and the grid. So that's more smart grid. How can you interact with assets that have been paid for within buildings by the private sector, and how can those assets help utility, especially during times of need, during peak periods or other critical periods where perhaps there can be a two-way flow of energy. That's going to take a number of steps, such as having equipment being able to talk with each other. And also there's liability questions as well. If the utility decides to do something that changes the operation of your system and that changes your economics, or something breaks, you know, who's liable and are you compensated? So those are details that need to be worked out, but these are big issues that are coming up in the near future. So in closing, you know, my goal here has been to, I think, illustrate that weather science has played a very enabling role for the growth of renewables, that growth has been very cross-disciplinary. It's been relevant to a variety of stakeholders, and also relies on very effective communication among the various stakeholders. This has also created, you know, lots of jobs for meteorologists across all sectors. We've lost a lot of employees who have gone on to work for developers or for banks, for utilities or manufacturers, which is great, And so they're smarter and smarter and smarter, and there's just more and more sophisticated analyses needed, and that's only going to continue. So the bar is going to be raised on weather intelligence. We think we're doing a great job now, but we have a long way to go, because there's going to be a lot more renewables and a lot more insights need to be understood. And then lastly, you know, the grid itself is weather sensitive, and more pressure is being placed on the grid. We're looking at the electrification of more things like transportation, EVs. We're looking at heat pumps and that sort of thing as well. So utilities have to wrestle with all of these real life issues. They have to wrestle with more renewables. They need more flexible generation. And the grid itself is subject to its weather extremes and outages and just overall sensitivity as well. That's going to require lots more input from the weather science community. That's a topic for another day. So I'll leave it at that. And so I'd be happy to entertain any questions, and I thank you for your attention.